Well, if you can be quiet, it goes a lot easier. Okay, when you take a derivative with respect to something, we need to remember what a derivative is. It's the slope of the tangent line. We're going to do the chain rule today. And the derivative is a rate of change. And you might have been hearing that all through your school years, but not really think about it. It's a ratio of two changes. So I can talk about the change in y as x changes. So if I say y equals x squared, now I'm going to draw y equals x squared, and I'm going to now change x a little bit, like maybe 1 unit. Well, then the y changes, doesn't it?
Oh, triangles.
That's the slope. So when I talk about the derivative operator looks like d dx, this means I want to see how y changes as x changes. And what's the derivative of x squared? You can just set it there. It's 2x. So if I go over another one, how does y change? It gets bigger. Okay. Ready? So we could talk about, and now we have to really talk about what this derivative operator looks like. The derivative with respect to x of x squared is 2x. We're okay with that. The derivative with respect to y of y squared, okay guys, is 2y. Notice how I changed the problem. If I change the y value a little bit, how does the square of it change? And the derivative of z squared with respect to not x, z is what? 2z. So what if I want the derivative of y squared with respect to x? That matters. So first I do the derivative of y squared with respect to that letter, which is dy. Then I multiply by the derivative of the inside function, the derivative of y with respect to x. I'm going to say this a lot, many days. So don't worry if you'll be able to do it today, but don't worry if you don't quite understand what's happening. Now, mathematically, Jack, I'm not really allowed to do this, but what could I do with the dy's? They could cross them out and does this statement here match the statement over here? Yeah, they're equal. So what I do when I do the chain rule is I take the derivative of the outside function and then multiply by the derivative of the inside function. And that's how I get it to work. These are for composite functions. But I have to really worry about with respect to. So if I have the volume of a balloon, which is 4 pi radius cubed, so it's 4/3 pi r cubed, if I change the radius a little bit, what's going to happen to the volume? It's going to change, right? Could increase, well, I could go down, right? And if r changes, v changes. But I could talk about what happens to the volume if I change the time. Well, if I change the time, the radius is going to change, right? And if I change the radius, then the volume's going to change. Because you could be blowing up a balloon and talk about the time frame. We'll get to those. Okay, Ben? We'll get to those later, the applications. Right now, this is going to be strictly a skill. And if I cross these guys out, you see I get dv dt. You have to think of those two ways, as a derivative operator and actually as a fraction. So let me say this again. If I change time, if I'm blowing up a balloon, so time goes on, then the radius will change. If I'm blowing it up, it'll increase. And if the radius increases, then the volume increases. That's the chain rule. These are for composite functions. So now let's look at my example I have here. And it's called the outside-inside rule, or you can call it the Tootsie Pop rule. The operator is this d dx. It's like a plus sign. When you see 2 plus 3, you say, oh, I know I'm going to add those and get 5. When you see this d dx, you know you're going to find a derivative. That's all it means, just an operator. Okay, so let's look at my little function here. This is hard to understand, so I'm not going to even talk about this today. But I'm going to talk about this function right here, y equals x squared. Well, actually, let's make an easier problem. Let's say y is equal to 2x plus 1 quantity squared. And I want to find the derivative of y with respect to x. No, well, you could right now we don't know how to do it, so we can multiply that out, but we're going to find another way to do it. Now, just think for a second. If I change x a little bit, what happens to this line? It changes a little bit. And if you change this 2x plus 1 a little bit and then you square it, what happens to the squaring? It changes a little bit. Okay? So there are two things happening here. You've got the squaring, you've got this. So all we know how to do is to square that out. So what is that squared? We're going to do it two ways, and because no matter how you do math, it's always got to work. Okay, Jack? What is it? 4x squared plus 4x plus 1. Everybody okay with that? So what's the derivative of y? I don't like y prime because it doesn't really say derivative of y with respect to x. It's assumed it's with respect to whatever variable that is. So what is that? 8x plus 4. Now let's try this a different way. Plus what? It's 2x. Are you questioning the squaring? This is the derivative of this. Does everybody believe that this line is correct? Okay, so now let's do this a different way, because if I do it a different way, I got to get the same answer, don't I? So let's try this by looking at this and saying, well, you know what? I have the power rule there. What's the derivative of the squared? dy dx equals 2 times, some of you just want to go to this directly, to the first power, right? Forget what's in there right now. So it's 2 times whatever's in there to the first power, but that's not right, is it? Is that equal to 8x plus 4? But what if I took the derivative of this little guy inside here? Multiplied it by the derivative of that, which is 2. Are these equal? Well, let's multiply it out. This is 4x plus 2 times 2, and that's equal to 8x plus 4. What's the derivative of this inside function? 2. That's the how you do it. If I change x a little bit, then this y value for 2x plus 1 will change, and then I'm going to square it. So guess what? There's even another change. You just multiply the rates of change times each other. Now, they're going to say, do some other alternate form with u's. Don't do that. Just do the chain rule. Because I want dy dx. Right, the operator is d dx. So if I come in here, I go d dx and d dx. And by the way, what do I get here then? I get what I call dy dx. You all call it dy dx. Because this really is the derivative of y with respect to x. But because we're so lazy, we call it dy dx. I should always call it the derivative of y with respect to x. But we don't, and nobody does. They all call it dy dx, or y prime. So let's do the first one on there. And I'm just going to extend my page a little bit. And so let's try this, and I'm going to use my Tootsie Roll sucker to talk about how to do this. When you walk out of here, you should know what you're doing. We're going to do this problem right there in the middle of your sheet. It's right here. It's 60. It's right. You can do it right on the front side. Then we'll do these. Then we'll do some right out of your homework. We did about 6 problems out of your homework. It's all on Schoology. Okay. We are going to come into implicit differentiation. I believe that's the next one, and that's when you're really going to understand this derivative of y with respect to x. Okay, guys, there's 2 functions here, right? Jack, Brian? 2 functions here. The outer function is the power of 60. Forget what's in there right now. The inner function is a quadratic. So I want to take the derivative of the outer function. It's the outside-inside rule. So derivative with respect to x of my y. Okay. Now here's how you're going to remember this. Doesn't seem fair. I get 2 suckers today. Can we give you guys a sucker? Yeah. Okay, so when I take the wrapper off, this is taking the derivative of the outside. Does the inside change? No. So this is going to be 60 times whatever's inside. That does not change. And then we do the 59th power. I can't expand that. I mean, I can with the cast, but I don't even want to. I'll probably get an overflow, actually. Then, if I eat just the candy part, not the chocolate part, does the chocolate part change? No. So that's what we're going to do. Now we're going to take the derivative of the inside. Well, what's the derivative of x squared minus 3x plus 4? 2x minus 3. And if you wanted to go further, and it's times the derivative of the inside of that, which is just the x, then what's the derivative of x? 1. We don't really write that, but there's really there was also an x in there. So you could do that times the derivative of that. And that's all there is. Because it's the what's the inside function? It's an x. You'll see it coming up. No. Let's not even put that in there. It's the derivative of x, which is 1. There it is. The problem is knowing when to stop. So we pick out a sucker. So I want you to remember, we'll have a little cartoon tomorrow, so I'm going to find it. That when you do the outside, it's a Tootsie Pop rule. The inside doesn't change. So that's going to be your biggest problem. So we're going to turn the sheet over. That's the answer. I can't really simplify it. And I don't care about simplifying it. Guys. 1. That's all I got left. So turn the sheet over and see if you can do the next one while I hand out the suckers. And then please clean up after yourselves, okay? Which obviously somebody didn't do. I know. You're welcome.
Thank you.
Mm-hmm. Okay, so turn it over and try. Recognize the 2 functions. I'll do it with you too, but try it.
Oh, 3x squared. No, you grab yourself. What color you want? I'm gonna use this bad color. Yes, I love this. Those are the worst.
Okay. Did I get to you guys? Hi. He's absent. Deal. Mm-hmm. Whoa. Everybody done? I know you get 1. Okay, let's do the next one. Turn it over. Now, you have to recognize the outside function. Can you give that to Ann? Yeah, you can eat those.
Sure.
Yes. So, okay, you guys, what's the wrapper? It's what? It's the 6th power. So it's going to be 6 times. Now, remember, does the candy change if you take the wrapper off? No. So this stays the same. The biggest mistake you're going to do is probably trying to take the derivative of that inside. Now, times See, I have no space, but that's okay. Do you remember the quotient rule? There. G times f prime all over g squared. Okay, so it's the denominator, which is 3x squared plus 2. Now, you guys are really lazy about your parentheses. Don't be lazy. It's not right without them. Times the derivative of the numerator, which is 2. Now, it's division. Yeah, it's division, quotient rule, so it's minus. Some of you think it's plus. You have to memorize it. Then it's, okay, so it's the denominator times the derivative of the numerator minus the numerator times the derivative of the denominator, which is, what's the derivative of this guy? 6x. All over the denominator squared. Never square that out. And there's no point in simplifying it.
So what? You write the entire like low E high high D low. I don't know like exactly how it goes. Oh, yep.
I can? Okay. That's a complete acceptable answer. Some people like to see it simplified. There's not a lot you can do, but it's possible, but it's rare, that this will all reduce, so it will reduce with the 3x plus 2 squared. But for those people who would like to see it, this is 6x squared plus 4. And the other part of the problem is, forget about that negative sign, but it's minus 12x squared, right? Minus 6x. The classic mistake of not distributing. Oh, yeah, I see it all the time. What? I just multiplied this out. So, for those of you who care, now you're going to want, if you're going to match the answers in the back, I guess you got to care. But honestly, that takes you too long. So, let's see, I got 6x squared minus 12x squared, so it's a negative 6x squared minus 6x plus 4. I don't think it's going to reduce. Okay, you guys, it won't be as complicated on the exam. 6x squared minus 12x squared is minus 6x squared. Minus 6x plus 4.
That's not squared.
What's not squared?
12x squared.
Yes, it is. Oh, did I read it wrong? No, I might have read it wrong. No, that's 6x. Okay. Let's try the next one, and then we're going to do some homework problems. Now, what you don't like about this is where that 8 is. So let's move the 8. That's one problem. Yes? Just a minute. Okay, I'm going to pull the 8 out. Hey, you guys in the back? Jack? Okay. Some people think, okay, 8x squared. That 8 I put outside because I can't do it very easily here. It's easier to see it here. Now, this is the angle. Some people think it's sine times that. No, it's the sine of an angle. So that's just an angle. That's an inside function. And we could do an easier one. We could do y equals the sine of x squared. That's my angle. What's the derivative of this? What's the outside function? The derivative of sine is cosine of, does the inside change? No. X squared times, and now the derivative of this one, which is 2x. Okay. So this is just going to be a little more complicated. I pulled the 8 out because even if I wanted to graph this to the 8th power, I can't put my graphing calculator sine to the 8th. It doesn't work. You have to break it the sine of x to the 8th power. So first I look and I see, what have I got here? I just got the power rule, right? So that's 8 times whatever's in there to the what power? 7th. Does the inside stuff change? No, think of the Tootsie Pop. Okay. Next function I run into, because there's 3 here, is the sine function. So it's times the derivative of the sine of that. What's the derivative of the sine? Cosine of this. Times, there's still an inside function left, the derivative of my inside function, which is this guy right here that I haven't read. You keep going till you get all the functions done, but make sure you stop in the right time. What's the derivative of this? Negative 45x to the negative 10 minus 16x. And I'm done. No, the 7th is over here. Because what I do first is I do the outside, which is the 8th. And I'm sorry, on the video you're not going to see me covering this up. I won't. I can highlight it. These are all times. Times. So first I do the 8th power, which gives me this one. And the inside stays the same. Then I do the derivative of the sine function, which is the cosine, and the inside stays the same. And do I have another color? Oh, look at that, I got another color.
No, use
I'm sorry, what? I didn't take it out. That's this guy. Because I'm first doing this. Let's do a simpler problem. Let's make it really simple. Y equals, and we actually, let's do sine squared of x. Because I can do that 2 different ways. Because it's really y equals the sine of x squared. So I do the outside function, which is a squaring function. So y prime is equal to 2 times whatever's in there, sine of x, to the first power. And then I have to multiply by the derivative of the inside function, which is cosine. Now, I can do that a different way. I could do y equals sine of x times sine of x. And then I could use the product rule. So I better get the same thing. It's the sine of x times the derivative of this sine, which is cosine of x, plus, then it's this one, sine of x, times the derivative of the other sine, which is cosine of x, which is 2 sine of x cosine of x. And I know that this is true because that's the product rule. Are they equal? Yeah. And if I wanted to find the derivative of 2 sine cosine of x, if I wanted to find this derivative, I would use a trig identity. Does anybody know what that trig identity is? That's the sign of what? Okay, this is one you should know. Maybe you didn't see it, but we need to know it. There's 2. Sine squared plus cosine squared is 1. That's one of them. And then the sine of 2x is 2 sine x cosine x. It's just a very convenient one to know. So if I asked you for the second derivative, we would do the derivative of the sine function, which is, so it's the cosine of whatever's in there. And it's composite. You may not realize it, but it's composite. There's a linear function in there times what? 2. I don't want to use the product rule on that. I mean, I can. No, it's much easier to do with the trig identity. But no matter what, I'll get the same answer. I may have to use a trig identity to show that it's the same answer. Well, let's look at, and who's got a book? Oh, she does. Let's look at some of the problems. Notice your assignment sheet is on the back.
If you have a trigonometric function by cosine or sine, can you just keep priming and just work it out and end up at 0?
The question is, what if I keep taking more derivatives of the sine and cosine? Will it ever go away? Noah? If I take the derivative of the sine, I get cosine. If I take the derivative of cosine, I get negative sine. If I take derivative of negative sine, I get negative cosine. And you say I'm going to cycle every 4 like imaginary numbers. But what if I have y equals x cubed? Well, if I keep taking the derivative, will I eventually run out? Will I eventually get to 0? My triple prime is 6, and the 4th derivative we write like that would be 0. So the powers run out.
Right height.
Yes. The trig, no, trig ones usually don't. Okay, so let's look at, I'm going to add a page, and we're on page 130, no, why do I say 130, 189? I'm going to copy the problems up here, some of them. I'm going to do this. And we are starting with 7. To be able to do 9 now.
What problem is this? What problem is this?
All these problems. This is on page 189. These are the homework problems. We're going to do 5 of them. Yes. Sorry, I didn't have any room. Yes. Now, I don't like the way 15's written, so I'm going to write it the proper way. There. Oh, we're doing great. Hey, don't you have your books? We go back to the other book, but I have put in a request to see if we can get a pilot for chapter 4. I don't know if it's written. I'm asked. I have to wait for a reply. That working okay? Press hard. You didn't get a book? I'll have to get one from another teacher because I don't have any. But they are online. Wait, which book are you talking about? The regular book or this little one? Oh, yeah, we own. Not yet. We will do all of chapter 3, and our first part of chapter 4 is out of the little book. Okay, this should not be too hard, should it? Ben's going to help me. Ben, what's the derivative here? Okay. Yeah. Now, you could make it 30. Who cares? Jack, you want to do the next one? Now, what I do is I don't like the way that's written. It's this. Then it's easier. Okay, ready? Okay. Guys? Yep. Time. You leave the inside alone, remember? To the what power? I'm doing the power rule. Times, and then the derivative of the inside, which is? Yeah. You can do this watching the election results. I think it's really close. Now, okay, guys? Oh, okay. Ready? Now, do you remember when we did, are we ready? Y equals e to the kx. Remember, and they said, remember what the derivative was? It was k e to the kx. And I said, just had to believe me for right now? Because it's e to the kx times the derivative of kx, which is what? K. Doesn't make sense that they put it where they put it. So how about number 11? Put your phones away. This is number 11. So what's y prime? You're like these. It's e to the 5x minus 7 times the derivative of that. That's the inside. Even though it's the exponent, it's the inside. This is not a power. This is an exponential. So it's times 1. Time. First I do e to the x, which is e to the x, whatever is in there, times the derivative of 5x minus 7. Some of the science books write e to the x as this. And sometimes it's easier to see that this is the inside function. I have the exponential, and my inside function is a linear function, not just x. Try 13. Of course, the inside changes if you chew on it. Jack, this is homework. You should be doing it. All of them. Good. How do we do the next one? The videos could be kind of funny, actually. What is that? Casey? What is that? That's the 1/2 power, right? Probably. So first you do the power rule. What's the derivative of something to the 1/2? Jack? 1/2. X plus 1 to the what? Negative 1/2 times, and then I have to do the derivative of this, which is what? Come on. Now, the only problem with this problem, I'm okay with this, but if it's multiple choice, you have to match it. So y prime, okay, I'm going to have, let's see, I have a 1 here and a 2 here. Did I copy it wrong? Yeah. I did copy it wrong, but that's okay. We can still do this. We'll do the one we have. We can do the right one. And then what happens when I do the negative 1/2? Negative 1/2 means that goes in the denominator. I don't like the 1/2. But you're right. I did copy the problem wrong. So let's do the right problem. That happens. There we go. Try that now. You should have it written down someplace. Try it. Watching does not do the trick. Try it. Yeah. I know, but now you're not going to know how to do it. Try it. Somebody want to go up there and try it? Want to go up there and write it?
It's going to be 1/2 x squared plus 1 to the...
Write it down. When you have a calculator, you can check it with.
Do we need the normal textbook to do this?
No, we're still on a roll.
What? Oh, we're still using our book?
We'll do the whole thing. You want to do it?
So, Miss G, do you drop one of our tests automatically? Or one of our 95% things?
I have dropped your lowest score, but I have to go back and do it because I had some makeups, but the rest of you all wanted to know, so I did it. I'll have to undrop and then drop again. It'll take a little time. It's no big deal. And then don't forget you can slide the board, but it's positive 1/2 right now. Oh, times. You get it? Times the derivative of x squared is not x, it's 2x. Yeah. Yeah. And then we're going to try 15, and then I'll give you a test back. Is that right? That's a 2x. Now, this is the type of problem that they're going to ask you to match. Okay, James? They're going to match. You're going to have to simplify that. The 2's go. And I'm left with x over the square root of x squared plus 1.
Oh no.
And you guys can look because the multiple choice, they are online.
That's a hard one, Miss Gombeski, isn't it?
Yep, let's do one more problem. Do you know what the derivative of the tangent is? Secant squared. No, I remember that. Now, what's my angle? It's 5x squared. Then you do times the derivative of this one, which is what? What's the derivative of 5x squared? 10x. Done. Now you have the first 5 problems done.